Okay guys, welcome to the second video on our vector note sheet. You can see that I've inverted the colors this time just to make things a little bit more interesting. And I like writing on the black background with these cool like fluorescent colors. In the last video we talked about how vectors represent a physical thing in the real world with magnitude and direction. So that could be distances and displacements. Um, it could be a velocity, it could be an acceleration, things like that. And we also saw some things that we could do with vectors, right? We could add them, we could subtract them, we could find angles between them. And we started doing the activity in class with them that had us using some of those techniques. In this video, we're going to look at another aspect of vectors, and that is vector components. So there's this idea that we can break vectors up into components, and that's a really useful tool that we'll see. We have a whole bunch of examples. And I would encourage you now, at the beginning of the video, to get your calculator out so that you can check along as we do the examples with the math. I would strongly encourage that. So vectors can be broken into components. Vectors can be broken into components. And so what are components? What are they, right? So I think the easiest thing to do here is to look at an example. Let's say that I just have some vector, and we'll call it a velocity vector. Off in this direction, we'll say it's 30 degrees above the x-axis, right? This will be my x-axis and my y-axis. So my velocity vector, v, is heading off in this direction, right? It's pointed in this direction, 30 degrees above the x-axis. I'm not picking that for any particular reason, just an example. And let's say it's just 5 meters per second is the velocity. So if I told you, head off at 5 meters per second in this direction, and you'd say to me, what direction are you talking about? And I'd say, okay, well, I mean 30 degrees north of the x-axis. You say, okay, I could figure that out, but that's kind of a little bit not intuitive. It's a little bit complicated for me to figure out an exact angle, and I don't really want to do that. But if you told me that I could go just in the x direction and then just in the y direction, I can do that because I'm familiar with the x direction, I'm familiar with the y direction. So that's another way to basically get to the point we're talking about. To create this vector, instead of saying let's go off at an angle, I could say, well, go this way first and then go this way first, and you'll get your vector in the end, right? As the hypotenuse of a triangle. So the components are essentially these legs here, these legs of this triangle that we've created. So we call this horizontal component because it's along the x-axis. We call that the x component. And I'll label it v sub x because it's the x component. And this one along the y-axis, I'm sure you can guess, we call the y component. We'll label that one v sub y. Now if I want to find the length of this v sub x, this x component, this leg of this triangle that we've created, I can use some basic trigonometry that we're familiar with to do that, right? So I'll write down our acronym, right? Sohcahtoa. Sohcahtoa. And what that stands for is that the sine of an angle, right? S is sine. The sine of an angle is equivalent to the opposite side of the triangle over the hypotenuse of the triangle. The cosine of an angle is equivalent to the adjacent side of the triangle's angle over the hypotenuse. And the tangent of an angle is equivalent to the opposite side of whatever angle I'm talking about over the adjacent side of that angle, the side right next to the angle. So we can use trig to figure out our v sub x, and what I can do is say, okay, well, I know the angle. I can see that, well, I know the angle and I know the hypotenuse, right? And I want v sub x. Now, I ask myself, is v sub x next to the angle or is it opposite the angle? Is it adjacent to the angle or is it opposite to the angle? And we can see it's touching the angle, right? So it's adjacent. So I want to look for something that has adjacent, a hypotenuse, and an angle. They all have an angle, and these two have hypotenuse, so not tangent because it doesn't have hypotenuse. But cosine looks like it'll work pretty well, right? So I can plug in the angle there. I can plug in 5 meters per second, my hypotenuse there, and then I'll leave me with A, the adjacent side, which is my v sub x, which is my x component of the velocity. So let's try that, right? The cosine of the angle, which is 30 degrees, equals the adjacent side, right? Adjacent over hypotenuse. The adjacent side is v sub x here, over the hypotenuse, which is 5 meters per second. And since I want v sub x, I'm going to solve for that. So I'll multiply this 5 meters per second over, and let me do that right over here on the line, right? So v sub x is going to be 5 meters per second times the cosine of 30 degrees, and I get that to work out to, let's see, cosine 30 times 5. I get right around 4.3 meters per second, right? My units carried through. So that is our x component of this velocity vector. It's the part of the velocity vector that points along the x-axis. And this is kind of an intuitive way to think about components, but if your vector was like a physical thing and you had like a light bulb or a light source up here shining light on it directly from above, the shadow on the x-axis would be the x component. And I could say the same thing about the y component if I was shining light from this direction, right? And directly from the side, it would create a shadow if my actual vector was blocking it. The shadow would be like my vertical component. If that doesn't make sense to you, that's fine to ignore it. That's just another way to think about it, right? I'm actually just going to get rid of this light bulb for now, in case it didn't make sense to you so it doesn't confuse you. If you liked it, you can rewind the video and watch that again, or just keep going. So we found the x component. Let's find the y component. So v sub y, right, is going to be something similar to what we did for our x. So I've got to find, now my v sub y is the opposite side, not the adjacent. So I want to match up opposite hypotenuse and angle. And so it looks like sine is going to work really well for us there. So sine of my angle, 30 degrees, equals my opposite side, which is v sub y, the thing I'm looking for, over my hypotenuse, 5 meters per second. Same process as the x component. 5 times sine this time of 30 degrees is approximately 5 sine 30. I get 2.5 for that when I plug it in my calculator. So we've gone through this process of applying trig to get our components, and we can actually generalize this, right? We did our original vector times either the cosine or the sine of the angle of the original vector. So that works for any vector actually. So let's say a vector A in the x component of some vector A is the magnitude of our vector A times the cosine of the angle of our vector A. And for y, the y component, it will be the magnitude of our vector A times the sine of the angle of our vector A. And we can apply that to a whole bunch of examples that we're going to do in just a second, but we can apply that to any vector. This is the general case. So one of the useful things about components is they give us another way, and a really convenient way we'll start to see as we use them, to add vectors together. So the results of when we find the components and add them can give us the magnitude of our vector that we get when we add them, which is called a resultant, or it could be the original if we've broken it down into components. Adding them gives us the magnitude and the direction. So it'll give us the magnitude and the angle, and we'll see how to do that. But let's just take a look at a whole bunch of examples now. So calculate the x and y components of the following vectors. So let me just set up some axes for us for each one of these, right? And it looks like all of these are going to be like north, south, east, west kind of things. So we'll do north, south, west's over here, east's over here. And before we even get started, let me just copy this down, and we might have to shrink it. Copy this down for all of our, let's shrink the original one first, yeah. We'll copy this down for all of our examples here. So, the first one, wow, change the color of that there. Okay, the first one, calculate x and y components of the following vectors. The first one is A is 7 meters at 14 degrees north of east. So what does north of east mean, right? If this is the east direction and I want to go north of east, I've got to go up this way above east a little bit, right? Towards the north axis. So like somewhere up here, and the vector is going to point that way. And we said that this angle between east and north is 14 degrees. And we said the vector itself, A, is 7, a magnitude of 7. So we can use our general rules, right? The x component is going to be vector times the cosine of theta. The y component is going to be the vector's magnitude times the sine of theta. So if I plug those things in, right, a sub x is going to be, if I could write it normally, there we go, a, which is 7, the magnitude, times the cosine, 14 degrees. And when I plug that in, I get right around 6.8. A little bit less, 6.792, 6.8, we'll round it to. And we didn't have, oh, well, we did have units actually, 7 meters, right? I should have had meters in here, 6.8 meters. So the y component, same process, magnitude of our vector times the cosine of the angle. Gotta catch myself here, right? Sine, because we're doing y component now. Sine of our angle. Let's see what I get for that. 7 times sine of 14 degrees. I get about 1.69, let's call it 1.7 meters. So those are our x and y components for this first example. Let's take a look at the second one. B is a 15 meter per second vector, so it's a velocity vector, and it's 25 degrees west of north. So now we're talking, the way to read these, right, is the kind of rule of thumb is look at the last direction first, and then go towards the other one that they talk about. So 25 degrees west of north means I'll look at north, and then I'm going to go 25 degrees towards the west axis. So something like this would be appropriate if it was drawn nicely. There we go. 25 degrees. And we're calling this vector B 15. Can I squeeze in the units? Meters per second. There we go. So x and y components of that, right? Oop, B this time. Let's do B this time. B sub x and B sub y. So both are going to start with the magnitude, right? The magnitude being 15 meters per second of our original vector. And then for the x component, we're going to do cosine. For the y component, we're going to do sine. And we're going to plug in our angle. Now, the angle here is a little bit trickier to think about. I can't just plug in, well I can, and you'll see that you get the same answer, but let's think about what we might want to plug in here more intuitively. We might want to plug in the angle between the horizontal x-axis and the vertical axis, right? So that would be, to get 90 total, I would need to add 65 to 25 to get that. So let's plug in 65 degrees right there, plug in 65 degrees right here, and see what pops out of there. Right, so 15 times the cosine of 65, 15 times the cosine of 65 gets me let's call it 6.3 meters per second. And then 15 times the sine of 65 gets me 13.6 meters per second. So those are my x and my y components for this second example here. All right. Now the other thing that we want to look at, back up here for a second, the other thing we want to look at is the directionality of our components, right? So if I take a look at this stuff and I blow it up for a second, not change its color, just blow it up, the components are going to be this way and this way. Or alternatively, you could think about them here and here. In either case, my x component points towards the left, right? My y component points up, but my x component points towards the left. My y component pointing up is positive because it's pointing up. But my x component is pointing towards the left, which is the negative direction. So I've got to add in this negative direction here. So that's an important thing to remember when we're finding the components of vectors, is to add the directionality to them. So let's take a look at this third example. We've got a vector c, and it looks like it's an acceleration, right? Meters per second squared right there, squared up there. And it's 27 degrees south of east. So south of the east axis, somewhere down here, right? The angle is 27 degrees. And I'd like to, let's see, it's c equals 17.5 meters per second squared. So let's find the components of that. Cx and cy both are going to start with the magnitude 17.5 meters per second squared. 17.5 meters per second squared. And then for the x, we're going to do cosine. For the y, we're going to do sine. And the angle is our 27 degrees. 27 degrees. So let's see what we get there. 17.5 times the cosine of 27. I get right around 15.6 meters per second squared, units carrying through, right? 17.5 sine of 27. I get right around 7.9 meters per second squared. And again, we've got to be careful, right? Because our x component was in this positive direction, but our y component points down. So our y component really is negative here. Y component is negative. So let's take a look at some more examples on the next page. So this is another application, right? This is the application we were talking about earlier of being able to add components of vectors in order to add the vectors themselves. So let's take a look at how we do that. The first step to adding up vectors via their components is to get the components that I need to add up, right? So I need dx, I need dy, the x component and the y component, I need fx, and I need fy, and for the x ones, I'm going to do the magnitude times the cosine of the angle. And the x one over here, right, is 35 meters is the magnitude, times the cosine of the angle. For the y's, I'm going to do the magnitude times the sine of the angle. The magnitude over here is 55 meters, and I should put units on here, times the sine of the angle. Let's see what I get those to come out to. So 35 cosine of 25 degrees, I get right around 31.7 meters. 35 sine of 25 degrees, I get 14.8 meters-ish, a little bit less, but it rounds. 55 times the cosine of 10 degrees, I get 54.2 meters if I round. And then 55 times the sine of 10 degrees, I get 9.6 meters rounding. So we've got a nice little table over here to just list our x and y components. So my x components are 31.7 meters and 54.2 meters. My y components are 14.8 meters and 9.6 meters. So the first step to adding the vectors via adding components is to calculate the sum of the x components and calculate the sum of the y components. So if I add these up, right, let's see, 30 and 50 is 80, that's 85, 85.9 meters for the x components added up. And then let's see, so this is going to be 4 and 9, 13, so 23.8 plus 0.6, right, gets me over 23, so into the 24.4 meters. So those are our added up components, and then I can sketch the x and y components and then the resultant down here. So if I've got the x direction going 85 units this way, I'm going to have a really big vector going that way for my x, right, for my x component. And then my y component, let's see, so 25-ish and like 100, less than 100, so a little bit less than a quarter of the length of this one. So I'm going to go maybe like this high just to estimate my y component. And I'll draw my resultant in red. Is going to be the tail of the first to the tip of the last vector that I drew, if I'm adding them, which I am. So that's what my resultant looks like, my resultant vector. So now we want to calculate the angle of the resultant and the length. So the length is pretty easy. You can probably see pretty quickly how to do that. So if my x was the 85.9 meters and my y was 24.4 meters, I can just use Pythagorean Theorem for this because I'm looking at the hypotenuse, right? So Pythagorean Theorem says a squared plus b squared equals c squared. For us, it's not a squared and b squared and c squared, it's x squared and y squared and r squared, right? So x is one of my legs, y is my other leg, and then my resultant is what I'm looking for. So what I can do is I can plug in the 85.9 meters, square it, plus the 24.4 meters, square it, and that's going to equal r squared. So let's see what I get when I do that. 85.9 squared plus 24.4 squared. So that gets me that r squared, remember it's still r squared, equals 7,974.17. And now I need to take the square root, that's meters squared, the square root of this stuff to get r, the magnitude of r. So the square root of that, I get to be right around 89.3 meters. So that is my resultant magnitude. But vectors need both direction and magnitude, right? So I want to figure out the angle between those two, between the x-axis and my resultant, this angle right here that we'll call theta. So again, thinking about Sohcahtoa, I've got now, I don't have a hypotenuse, but I'm looking for that. I'm looking for the angle of the hypotenuse. But I do have adjacent and opposite sides, so it's looking like my tangent function is going to be good for that. So tangent is the tangent of theta equals the opposite side over the adjacent side, right? So the tangent of the angle equals, my opposite is my y component, so that's 24.4 meters over the adjacent side, which is 85.9 meters. My units cancel, that's good because I'm just looking for a number of degrees. So a lot of students at this point say, let me just divide the numbers and that's my answer. And if you did that, it would be wrong, because what would happen if I divide those numbers, let's see what I get. 24.4 divided by 85.9, that gets me 0.284, and you might be tempted to say, there's my angle. But that's the tangent of your angle, that's not your angle, really, yet. What I need to do, I need to solve for the theta, the angle variable. So to do that, I need to do the inverse tangent. I need to undo the tangent function on both sides, right? I need to inverse tangent both sides. So if I do that, then what I end up with is that my angle is about 15.9 degrees if I round. And that is all the information that we can get about the resultant vector, its magnitude and its angle, from adding its components. So let's take a look at this last example now. Very similar to the one we just did, just that now we're dealing with 3 vectors instead of 2. So let's go through it quickly. There is one other tricky part about this though, right? And this actually brings up a good point that I meant to mention earlier in one of the examples where we had the 25 degrees and we used 65 degrees instead. Our rule, right, our rule where we did that the x component is the magnitude times cosine of the angle, and the y is the sine of the angle times the magnitude, assumed that whatever vector we were talking about, its angle is being measured off the horizontal axis. And that's important because when we're using these cardinal directions, we've got to check and make sure that our vectors are really being measured. If we're given information off the horizontal axis, essentially, or if we're given information off the vertical. And if we're given information off the vertical, we've got to flip-flop and find off the horizontal, otherwise our rules won't work. So let's see what we've got here, right? These first two, north of east, if I've got my north of east, would be off the horizontal, so we're good there. South of west would be off the horizontal, so we're good there. West of north though, right? North and then going west, that's an angle here off the vertical, so that's no good. That's not going to work for our rules, but it's easy for us to make a fix to that, right? So we want to figure out what's the complementary angle to get up to 90 degrees. 35, 90 minus 35, 55 degrees, and that would just flip-flop these. That's north of west, right? Going north towards the north axis from the west axis. So we're going to use the 55 and not the 35 when we work out the components. So let's work out the components quickly there, right? Let me write them all down. Gx, Gy, Hx, Hy, Jx, Jy, This is going to be 1.5 meters cosine 50 degrees. This is going to be 1.5 sine 50, sine 50. Whoa, that's awful. 50. 3 meters cosine 70. 3 meters sine 70. 4 meters cosine 55, right? And 4 meters sine 55. Okay, so let's plug those in our calculator, right? Let me do this. 1.5 cosine 50. I get that. That's 0.96 meters. 1.5 sine 50. I'll round it to 1.1 because we're going to just keep one decimal spot, meters. And I guess if I'm going by that rule, then this last one would really round up to 1.0, right? Just keep one decimal spot. 3 cosine of 70 is 1.0 if I round. 3 sine of 70, 2.8. 4 cosine of 55, 2.3. And 4 sine of 55 is 3.3. Now, another tricky thing to check, right? Which direction are my components facing? Are they negative or positive? Cosine, right? This one was north of east. Both my components are in positive directions, so we're good on both of those. This one was south of west. So, right? South to the left, that's negative. Down, that's negative. So both of these are actually negative numbers, negative components. West of north, or north of west, right? Depending on which way I want to look at it. Vertically, I'm good, so my y component's positive, but my x component is negative because I have to go over this way for that, right? So let's write all those down in our table. We've got 1, and then we've got negative 1, and then we've got negative 2.3 for all of our x components here. We've got 1.1, we've got negative 2.8, and we've got 3.3. So 1 minus 1, 0, so I'm left with negative 2.3 over here. This guy's going to get me, let's see, 1.8 and then 1.7, negative 1.7. That would get me to 2.6 and then minus 2. So 1.6. Let me just check that really quick. I'm pretty confident on that, but let me just check. Yep, 1.6. So those are meters. My resultant, right, r squared is going to be my x squared plus my y squared, Pythagorean Theorem. Square root of both sides, r equals the square root of x squared plus y squared, which is the square root of negative 2.3 meters squared plus 1.6 meters squared under square root. Let's see what that comes out to. Negative 2.3 squared plus 1.6 squared under square root. I get 2.8 meters. And then our tangent rule, right? In the end, our general tangent rule was that we took the inverse tangent of, right? The inverse tangent of this stuff, which turned out to be 0.28. So our general tangent rule is that the angle equals the inverse tangent of the y thing, the y component magnitude, over the x component. And it's not just the magnitude, we should include directions there too. So inverse tangent of the y 1.6 meters over the x, negative 2.3 meters. Units cancel, that's a good sign. So I'll do inverse tangent of 1.6 divided by negative 2.3, and I get negative 34.8 degrees as my angle. And I don't really have much space here, but I just want to draw a quick sketch of that for us. Negative 34, that's fine. That's just, if 0 is always my positive x-axis, so negative 34 is just below my x-axis, right? Negative 34.8, I won't write the 0.8. And the magnitude of that vector r is 2.8 meters. Okay, guys, I hope this video was helpful. And if you have questions on any of this stuff, please be sure to ask them in class. All right, have a good night.